Shantanu, you are the host now, okay?
Hello, Saurabh. Did you say anything?
You are the host now.
Yeah. Okay. Yeah, yes. Yeah.
That's the last one. So what do you expect in this case? So for example, AND operator would, for example, this will be first. And since 3 is a true value, it moves to the second operator. Now it returns the last one. And what about if you work on this logic here? Let's see. Since the first operand is false, it returns the first operand. In this case too, the first operand is false, so it returns the first operand. Now, since the first operand is true in this case, AND operator moves to the second operand and returns it. In case of 1 and 1, the first operand is true. Therefore, AND operator moves to the second operand and returns it. You might notice that this is the same result as we got in the conventional logic. So I hope you had a good understanding of the AND operator. Now we'll move to the next operator in logical operators, that is the OR operator. Before wrapping up, let's have a look at some of the examples.
Yourself.
You want to check something like if 3 is less than 5 and also 5 is greater than 3. We can do something like as 0 and 3. Also we can do something like true and false. So these are some of the examples of logical AND operator. Let's move to the second operator in logical operators, that is the OR operator. So the definition of OR operator in Python is
Am I audible?
not found, it returns the last one. Let's look.
This is currently working. Hello. Am I audible?
Yes.
Okay.
Yes.
Okay, good. So I am Shayantan. So I'm actually a TA of this course. So today we will mostly see, so I'll take today's class. So today I'll just introduce this asymptotic notations and see these recurrences. So I mean, these are very important for the coming week, I mean, for the even the whole course, because most often, I mean, almost in every case, we'll be analyzing our algorithms in terms of either of, we'll analyze the algorithms in terms of this asymptotic notation, whether it's big O or omega theta or something like that. And in many cases, this running time that will be like expressing as these order notations. So they will often come from a recurrence relation, right? So yeah, so maybe I mean, how many people are taking this course? I mean, sorry, I took the last tutorial, but it was not for the whole. So how many people are actually taking this course? Hello, am I audible? Is this line not connected?
Yes, you are audible.
Okay. Yeah. So if like if it's any point you are not listening and all, so I mean, please like tell me. I mean, sometimes internet may disconnected, and there's a problem with Zoom. Like if it might get disconnected, and only after a certain period of time it will actually seem getting disconnected. So I mean, if somebody speaks up, I mean that. Sorry. Yeah, maybe we wait for a couple of minutes and then we'll start. Excuse me, just 1 second. Hello. Is my screen visible?
Yes.
Yes, sir.
Okay, good. So how many people are taking? Yeah, 28 has come. So how many people attend? I mean, roughly more than 40, right? I mean,
50.
Oh, okay, okay. Then maybe we wait for a few minutes. Oh, so is there a class before this class? No? Or this is the first class for both of these batches.
No, for some people there is a class before this.
Oh, okay, okay. Maybe we start, if that's okay. Or maybe wait for 1 more minute and then we'll start. Okay.
Please make sure that you share the notes, okay? It'll be really useful.
Yeah, it will be uploaded. Yes.
Okay, thanks.
Anyway, this way, yeah. So one more thing. I mean, already there have been some video lectures. Saurabh has already posted that links to the video lectures in the class web page. Okay. So please check them out and see them. Okay.
Okay.
Yeah, maybe we start now. Okay. So yeah. So mostly not happening in the whole thing. Yeah, so I think this is visible, no?
Yes, sir, it is.
Okay, so maybe we start. Okay. Why is it not? Oh. Maybe I stop the share and then it's opening. Yeah. So it's again visible, right?
Yes.
Okay, so we'll first start with the definitions of these asymptotic notations and then we'll see some examples. And finally, we'll see how the various recurrence relation can be expressed as as a solution to these asymptotic notations. Okay, so maybe I start with the most famous, like not most famous, but I mean one of the most. It is this big O notation. Big O notation. Okay, so yeah, so it's like big O. Okay, so I mean let's see the definition first. So big O of Gn is, so maybe I write it first and then I'll explain it. So there exists three and okay. So let us assume that our f Gn is a function of n. Okay, so by big O of Gn, what I mean, big O of Gn denotes a set of all functions fn such that like fn is at most c times Gn Okay. For some C and for all n which is at least n naught. So what does this actually mean? Okay. So, so the intuitive idea is big O of Gn represents a set of functions which are like upper bounded by this thing. So for example, so maybe I draw, I mean, say order of n, right? Right. Maybe I'll draw the diagram first. I think it's better. So maybe this is the diagram. So suppose there is this function fn, okay, and there is a function. I mean, gn is such a function such that like this is this, right? So my point is beyond this point, right? Cgn is always more than f of n, right? So for this case, right, this is this eta naught, right? So for example, right, let's see an example, I think maybe, right? So for example, let's take a function, right? Say I take a function, say maybe this. Let's take a function. So for example, right? So let's take a function is 3n plus say 8 or something, okay? Right? So so can you give me what can be like order of f of n based on only on these definitions? Anybody?
N.
Yeah, you're right. So how is it happening if we follow these definitions? See, 3n plus 8, right? It is always greater than, it is always less than equal to 4n when n is greater than equal to 8, right? I mean, this function's value. So when I go over n, any value of n greater than 8, the value of 4n is always at least as large as 3n plus 8, right? So 4n gives me an upper bound of fn, right? Is this okay?
I had a question. So are you assuming that all of these functions are always positive?
Yes, yes, yes. Always positive. I mean,
Okay.
not some weird kind of thing. I mean, we'll go there. I mean, once we find, I mean, once we wrap up this definition, so we'll see one case where these things plays a role. But for now, for the moment, let's assume that it's all are like well-behaving functions. Okay, we'll see an example later. Thanks for pointing out. I mean, okay. So my point is here, what is the value of C? C is 4, right? So there exists a C, I mean, in this case 4, such that if we multiply 4n, it is getting, it is giving me an upper bound on my function. This is my function fn, right? I mean, this is this definition, right? I mean, maybe I write it here. So fn. And this is happening when n is greater than equal to 8. Now, for example, so for this case, n naught is 8, right? N naught is 8. So after I have reached 8, this is actually dominating, right? This is say 4n, and this is my 3n plus 8. This is my n naught, which is for our case 8. So after n goes above n, I mean, n is greater than equal to 8, all this part of this number line, 4n function actually dominates 3n plus 8, right? But before that, say n equal to 2 or 3, in that case, right? Say n equal to 2, right? I mean, it's like 6 plus 8, 14, right? 14 is not less than 8, right? This is not true, right? So anything can happen before n not value. You understand my point? So my point is once the parameter n goes above this threshold n naught, one function, this CA of Gn function actually dominates this function Fn. By dominating, I mean its value is at least as large as the other function, right? But before this particular value of like threshold, I mean, we cannot say anything, right? Up till now, is okay? So order notation, I mean, this big O notation gives me an upper bound, right? Hello? Is this okay?
Yeah. So when we say n, you mean n is an element of this set?
N is the natural number, right? I mean, n is the size of
but like, so in your example, big O of Fn, we will say
Yes.
that n is an element of big O of Fn, the way you have defined it.
It is a function. Yes, it is a function. I mean, Fn is my like order n, right? I mean,
No, but order big O of Fn is a set, right? You have defined it as a set. Set of
yeah,
all
yeah, it's an
functions
element. Yes, of course.
dominated
I
by.
mean, that n
Exactly.
is of that function's value, right? I mean, yeah. I mean,
Okay,
that is
understood.
implicit, right? I mean, so in that case, I can actually write like 3n plus 8 is order n, right? So when we write things like that, right, we generally write this. So by implicitly we are assuming so there exists a C and n naught such that this thing holds. Okay, we generally do not specify this value, but we know that there exists some value, right? And this is this understanding of asymptotics. So initially, right, so as we have seen in this example, until n naught is like 8, like 4n is not dominating 3n plus 8. But this is the study of asymptotics. The idea of asymptotics is when n goes large enough, what is the behavior, right? So we can actually safely like discard this any value before n naught. So the idea is when n, the parameter on which these functions are depending, when it is large enough, what is the behavior in that scenario, right? So in that case, this big O basically gives you an upper bound, right? And whenever we say some statements like this, right, implicitly we are assuming that there exists a C and n naught. Okay. Hello. Is this okay?
Yes, sir. Understood. Yeah, understood.
Acha, so anybody, if you have any doubts, so please unmute yourself and shout out. Okay. I mean, it's online, so I cannot see people's face, but I mean, please shout out in this case. Sorry, if you have any doubt. Excuse me. Someone's talking something. Sorry.
Sir, can you show the definition again?
Yeah, sure. Okay, so we'll go to the next part. Okay, so these are very standard things. So there is a very nice write-up in this CLRS book. I'll probably give you the last CLRS. This Corman, Laserson, Rivest, and Shamir's book. I mean, yeah. So let's go to this next definition because, yeah. So we'll see what is a big omega notation. Okay. Okay. So again, I'll give you this definition first. Okay. These functions, there exists a C and n naught such that 0 is equal to Cj less than equals to Fn for all n greater than equal to n naught. Okay, so the definition of this big omega is very much similar to the big O notation, except the fact that this ordering is reversed in the sense that, I mean, this condition is reversed, right? So for big O, it was like 0 less than equal to Fn less than equal to Cgn. But it's the other way around. Do you understand? I mean, again, if we draw this picture, I mean, it will be clear, I think. I mean,
Do you mean G of n is big O of f of n? Then f of n is omega of G
yeah,
of n.
yeah, yeah. It's a complement. Yeah, yeah. It's a complement. I mean, yeah. So if you draw this picture again, right? I mean, this is f of n, this is c of g of n, and this is my n naught. So as soon as the parameter n reaches the value of n naught, this function dominates this function, right? So in some sense, this is giving me a lower bound, right? So big O, I mean, roughly, intuitively, big O gives you an upper bound. I mean, right, I'm not writing the whole thing. UB means upper bound, and big omega gives you a lower bound. I mean, it is kind of bounding this value, right? It is bounding this value by lower thing, right? Okay. So maybe we see a short example. Maybe that will be clear a bit more. Which example shall I give? Okay. Okay. So I'll just quickly go through one small example and then I'll give you a bigger example. So for example, right? So let's consider this function, right? Fn equal to, oops, what happened? Fn equal to 5n square, right? So can you intuitively see this picture and say what will be the omega value? What will be like omega of, I mean, right? So what is like, for example, what is like 5n square? What is the omega of this thing? I mean, what will be here? I mean, any guess?
N square.
Yeah, yeah.
N square and raised to 3 by 2. Anything.
Yeah, yeah. So, but here when we write it, I mean, you're right. I mean, anything smaller than n square is good. I mean, n log n or. But whenever we are giving these bounds, we actually prefer to give the most tight bound, right? Because I mean, these are generally comes from this analysis of algorithms. So we are interested in giving the as accurate definition, as accurate bound as possible, right? I mean, you're absolutely right, but we generally try to give the most closest bound. So for this case, I mean, we just need C and N naught such that this thing holds, right? C of N, right?
Yeah. C of n square is less than or equal to 5n
Right.
square.
So I mean, you can do that, right? I mean, yeah.
1/5, 1 by 5.
I mean, yeah, yeah, yeah. So I mean, this is okay, right? So I'll just give you a slightly trickier thing. So example 2, right? So yeah, so my example is this thing. So suppose my Fn is something like of this form, say 100n plus 5, and I want to prove that this is not equal to omega n square, right? So n square is not a lower bound of this thing. You understand my point? Is this question clear?
Yes, sir.
Okay, so maybe we see a small thing. So what is the proof? So if this is suppose we will prove by contradiction. Okay, so that means there exists a C and N naught, right? Such that, right? So 0 less than equal to C of n square. I mean, this thing some constant multiple, right, is less than equal to 100n plus 5, right? But because this is lower bound, right? So this will come here, right? So if we actually, so this thing I can actually upper bound by say 105n, right? This is true, right? So I am actually saying that Cn square is less than 105n once we reach some n naught I mean, once n is greater than equal to some n naught. But as you can see, I mean, this implies that something like this of this form, Cn minus say 105n is less than equal to 0, right? And since we are assuming in like n is greater than 0, right? This implies that n is less than equal to, right? N is bounded by some constant. But here we are assuming that n is a free variable, right? N can obtain any kind of large values, right? So this is not possible. This implies that our assumption was not possible, which implies that I mean, like 105n is not omega n square, right? Is this okay? Hello.
Yes, sir.
Yes, sir.
So basically, I mean, roughly big O gives you an upper bound and big omega gives you a lower bound. So far, so good? Hello.
Yes, it is fine.
So a natural question is, I am giving given a function by big O, I am giving an upper bound, and by big omega, I am giving a lower bound. So does that exist that is somewhere in between, right? So here comes this theta notation. Okay. So maybe I'll write the definition first. So theta of Gn, right? Functions. Right, so maybe I'll draw this picture first and then maybe I'll just okay. Start here. I mean, it's not exactly. You understand this point, right? So let's, for example, like this is my theta to Gn, this is Fn and C1Gn. So basically, my function Fn is somewhat bounded by this parameter. So it's kind of so there is a something called sandwich theorem. I mean, if anybody knows. So this function is somewhat sandwiched between them. So at any point, once n is greater than equal to n naught, any value of Fn is upper and lower bounded by some multiple of this function Gn. So in some sense, Gn is like upper and lower bounding this function Fn, which means that it is, and C1 and C2s are constant, right? So it is giving me a very accurate representation of my function, right? You understand my point? This is not a upper bound or lower bound, as somebody said, right? Anything like n square is omega n, right? But there is a large gap, right? N and n square, because we know that n square is omega n square, right? So our goal is to give you give any as tight bound as possible, right? So theta notation actually achieves this thing, right? So maybe we see an example. I think that is like best. I mean, explain this thing. Excuse me. So for example, suppose let's keep this thing, right? Say I'm considering this function Fn. Fn is say n square by 2 minus n by 2, and I want to give a tight bound of this. Now note that n square by 2 minus n by 2, right, is strictly less than n square, right? Because n square by 2 minus n by 2 is already less than n square by 2, right? So it's strictly less than n square, less than equal to n square. And on the other hand, I mean, it is certainly less than n square by 5, right? Because I mean, anything is like, so one thing I'll also tell later, So any n square is of course greater than n. Simultaneously, n cube is always greater than n square. I mean, you understand my point? Once n goes large enough, right? N cube will always dominate n square or something like that, right? I mean, my point is, as long as I can increase this power on n after a certain threshold, which we call n naught, n cube will always dominate other functions whose power is smaller than 3, right? I mean, this n naught. So n cube, so once n is greater than or equal to some n naught, I mean, n cube is always greater than like this n to the power 2.99999, something like that, right? Once, if we take large enough n, and we are only considering asymptotics, we will only consider large values of n, so we do not actually care about this threshold value till threshold, right? So I mean, of course, I like, so for this function fn, I can upper and lower bound it as terms of n square, right? So what is this case? So c1 is 1 by 5 and c2 is 1, right? And I think if you take n naught should be something like 1, right? So this bound actually, this condition actually is holding, right? Is this okay? Hello, am I audible?
Yes, sir.
Yes,
So,
sir.
So you
yes, sir.
understand my point, right? I mean, it is sandwiching these both parts, right?
Yes, yes.
For n greater than or equal to 2, yeah.
Yeah, I mean, okay. I mean, maybe it's greater than or equal to 2. I mean, please check this constant value. I'm not checking. I think maybe it's 2 or something. But you understand my point, right? After a threshold
Yeah.
reaches, I mean, this n square, this function fn is upper and lower bounded by n square by 5, lower bounded by n square by 5, and upper bounded by n square, right?
Yes, understood.
Okay, cool. Okay, so I'll just give you a small like not counter example, but maybe this example one. So can we prove that? So maybe this is an exercise, okay? I mean, okay. So this kind of a homework kind of thing. So just prove that n is not
Sir,
equal.
can you be a bit louder? It's not audible clearly.
Oh, is it the case? Hello.
Yes, it's okay now.
Maybe I'll increase this thing. Is this okay now?
Yes, yes, it's okay.
Yeah. Yes.
Okay. Please, I mean, say. I mean, I do not. I cannot understand. I mean, yeah. So please feel free to say any. So for your homework, please do this problem. So prove that n is not equal to theta of n square. I mean, it's just definition. Just unravel the definitions. I mean, it will follow. I mean, this is just a practice problem. Okay. So far so good. So again, I'm just like giving you a summary. So first we saw big O notation. So roughly big O notation gives you an upper bound, right? And similarly for big omega notation, this is a lower bound. And of course there is a lower bound and upper bound. So we want the function to be as accurate possible, right? So there is the function of theta, right? And of course, since we are considering asymptotics, I mean, it may be the case that some function dominates the other functions once the value of n reaches a threshold, which we define as n naught, right? But since we are asymptotics, it doesn't matter, right? Right? Is this okay?
Sir.
Yeah. So there are some two small definitions. So there is something called little o of this. This is little o. Little o of Gn is actually set of all functions fn such that for all c and n naught, right, 0 less than equal to fn less than cgn. Okay. I mean, initially like this will be okay. I mean, this is previously was a less than equal to, but now it is strictly less than. Okay. N is greater than
It's
equal.
for all C and N naught.
No. For all C, there exists an N naught.
Right.
Right. Thank you. Yeah. So one intuitive way, right, is to express it. I mean, equivalent way to express it is of this form. So if we take limit n tends to infinity, right? So Gn by Fn will be infinity, right? I mean, Fn strictly dominates. Gn strictly dominates Fn. That's why it is strictly less than, right? So when we take n sufficiently large, I mean, Fn will go way beyond it. Gn would go way beyond Fn, right? So as you can like guess, there is also another slightly related definition, which is little omega. I mean, it is just the other way around. Omega of Gn, right? It is like this thing. So Fn, right? So for all C, there exists n naught, right? Such that 0 less than equal to Cgn, strictly less than Fn, and for all n greater than equal to n naught, right? So I mean, like similar to this definition, I mean, I can actually say the same thing. So limit n tends to infinity, right? Gn by Fn, right, actually goes to 0, right? Because this is a strict term, right? Right? Hello?
Yeah, understood.
Yeah, so I mean, say, sorry, right? So for example, like, so n is omega n square, right? I mean, like if we take n by n square, limit n tends to infinity, goes to 0. I mean, this is gives you a strict thing, right?
Yes, sir.
Yeah, so maybe we'll just and there is also another definition.
Sir, once scroll up, sir. One second.
Yeah, sorry. Yeah.
And
No,
also,
this is the other way around, no?
Yeah,
Can
this should
you
be
do-
little, right?
Huh? It will be the other way around. I mean, I just messed up.
Little of n square, right?
Yeah, it is the other way around. I mean, n square would be omega, little omega of n, right? I mean, that was what my one. What is happening? Right. Yeah. Thank you. So, like n square is little omega of n, and as somebody has pointed out, n is little o of n square. And they're equivalent, right? I mean, they're just the opposite way around, right?
Yeah. So one more thing, like log x is small o of x. That like other than that, can you give us some more examples of little or small omega notations? Little omega notations, because like in some sense it feels like that there would be some dominating term of x or n in that. So it would
But
be
anything other than that, that will cancel. That will like dominate, right? I mean, I don't understand. I
some
mean,
non-polynomial examples of these notations if you can give. Like in some sense up till now, if the n term has a higher degree, we are getting these notations. Other than those
So,
examples,
like log x
an
to the power
example
of n is small o of any power, any exponent of n.
okay.
Any
So
constant
let's
exponent
see
of n.
this. So log cube n, right? Log
yes,
cube n will always be less than, say, log 4n, right? Once we go some n is some large thing, right?
yes, but again, this is
So
like
this is still polynomial,
in some sense
technically.
anything other than polynomial and log x. If there is some example,
So this is n, right?
Okay.
So for example, root n, log cube n would be less than
Yes, yes.
root n.
Okay, so maybe I'll so just let me give you another definition. I'll just explain this whole thing. I mean, I understand what you're like claiming. So you want to some
Yes.
sort of order the whole possible functions kind of thing, right? Is this what you're
Yes.
saying?
Yes, essentially.
Yeah, yeah. So just give me I'll just give you a small definitions and then so there is there is a notation which is called sim. I think it is SYM or SIM. I'm not completely sure about the spelling. So a function fn, right? It is sim of gn, right? If limit n tends to infinity, fn by gn is 1. It means, for example, say fn is say 3n plus 100, okay, and say gn is say 3n, right?
Sir, on left side, it should be C or 1.
Now it is 1. I mean, that is the point. I mean, this dominating coefficient of dominating term should be same. I mean, there should be another thing. I mean, it will be useful. So maybe I'll give you a small exercise here. Maybe I'll just give me 1 second. So there is a definition of this thing. For example, I mean, this is an exercise. I'm not doing it here because I mean, we'll see this this thing. So maybe this is an exercise. We can prove that this is sim of 4 to the power n by square root pi n. This is actually a example of,
Stirling's approximation.
yeah, I mean, we can use, I mean, this is a problem. So actually in the web page, though, there is a problem set on this asymptotics. So this problem is coming from that problem set. It's here, they are in problem 3 or 4. But please try this. I mean, yes, you are right. We have to use Stirling approximation. So I mean, Stirling approximation says that n factorial is like similar to like root 2 pi n into n by e to the power n, something like that, plus some lower order term, plus some term here. Okay. So if you do this example, I think it will be clear. So now coming to your question, right? So basically, see, constant function. So any constant function, I am actually writing it as 1. Okay. So constant function is of course less than log n, right? Then say square root log n or something. Then maybe say, I don't know, maybe log square n or something, right? Then say n, or say square root n or something, say n, right? I mean, I'm just continuing from here, okay? Less than, say, n log n, okay? Say, of course, which is of course n square, say, which is of course say 2 to the power n. Of course, I mean, it is like 4 to the power n or something like that, which is less than n factorial, right? I mean, you understand this thing can go on. Now, there are a couple of interesting things to note, right? So one interesting thing is that here I am writing it as log n, but before log n, I mean, there can be log n also, right? Hello? Hello?
Yes, sir.
Yes,
Yeah,
I
yeah.
understood.
Similarly, there also be some sort of thing like that. I mean, square root, right? I mean, somewhere in between, I can actually give you log n to the power 1/3, right? It is square root, right? To the power half, right? Similarly, this is log square, but I can actually, so somewhere here, I can actually give you like log of 1.5 or something n, right? Similarly, between there also I can give, but this is more or less like ordering. You understand my point? This various definition. And somewhere here I can actually give you log star n or something. And similarly, in between square root and n, right, I can give you n to the power 3 by 4, right? Somewhere here, right? Again, somewhere here, I can actually give you, say, n log n log n to the power, say, 1 by 3 or something, right? Similarly here, you understand my point, but this whatever I have written here, this is more or less a order thing, but you can define as much functions as you want in between them, right? You understand my point? So instead of log n, maybe you define like log n, right? Where's my pointer? You understand my point? Hello?
Yes,
And
I
similarly for
understand.
one third, I mean, you can put any arbitrary thing, right? I mean, similar, but this is whatever I have written on initially in blue. I mean, this is more or less the idea, right? So is this okay? But you can fill it up as much as possible and all, right? So is this okay?
Yes, sir.
Okay. Okay. Good. Okay. So just give me. So I'll just have some water. Okay. So this is more or less our introduction to asymptotic notations, right? Now we'll proceed to this various how to solve these recurrence relations. I mean, how to express this recurrence relation as these order notations, right?
Sir, you mentioned that if we need to use the most, we need to use the most tight bound whenever we use any notations.
Yeah, that is more or less the idea. Yeah.
Okay, so in previous, can you scroll up in the omega n example?
This
Below,
small
yeah.
little omega or big omega?
Yeah, it's little omega. So in that omega n square is equal to omega n, right?
Right. Right.
Can we? Shouldn't it be n log n or something like that?
Yes. Yes.
How
Yes.
do we?
No.
how
No.
do
No. So no. There is no as such consensus how tight we should be, right? There is
Okay.
no. I mean, there is no consensus. It is depending upon the context and all. I mean.
It's
So,
not
so
valid
if
in
you say
small.
log n, somebody can say no, give it log n to the power 100, right? I mean, it's a never-ending process, right? You can name any natural number, you can put log n to the power that thing, right?
Yeah, that.
I mean, n square would always dominate in n into log n to the power any number, right? Any natural number,
So
right?
even better would be n to the 1 plus epsilon, where epsilon is
Yeah.
as
I
close to
mean,
1 as you want.
this is like this is more of an understanding thing. I mean, you can always do that kind of thing, but this is a consensus. I mean, we are not writing n is omega n square kind of thing. I mean, this depends upon context. I mean, maybe I should not have exactly said in that form, but it depends upon context, right? When I can give you, so suppose you are designing an algorithm, okay?
Little
Sorry, I couldn't hear. Hello.
in little omega and little o, it should not be valid. That it should be tight.
What type?
It should be tight bound.
No, how tight? That was what we were discussing, right? I mean, n square would be omega of n into log n to the power any natural number that you think, right? If you take n naught will be in that case n naught would be large, right? You understand my point? I mean, there is no, it's a never ending process. So this is a general consensus kind of thing, right? I mean, you understand my point? But anyway, when you are designing an algorithm, right? Suppose you have designed an algorithm, suppose its runtime is ordered n. So you can always say its runtime is ordered n square or n log n, right? But when you are designing algorithm, the general idea is I want to give the algorithm which is as better as possible. I mean, I wanted to mean in that sense. I mean, you understand my point? Suppose you have designed an algorithm and suppose this algorithm is ordered n. It's a linear time algorithm, right? You can of course say it is a quadratic time algorithm, right? But that is a wasteful thing, right? I mean, when you are designing something, you want to give it as good as possible, right?
Yes.
Yes. I mean, that is what I wanted to say. Okay. So maybe I'll jump ahead. I mean, yeah. Okay, so I'll see these order notations, this recurrence relation and how to express them as order notation. So I'll actually okay. So I'll actually show you 3 examples how to solve them, and it turns out that all of them will be used somewhere later in this course. Okay. So first I'll search. We'll do this this thing. This order notation T of n is T of n by 2 plus order plus 1. So this is the recurrence of like binary search. Okay. Now, given a relation, so I want to so this is, suppose you have designed an algorithm, right? And somewhat this recurrence has come up, right? So you want to say something. What is the order of this thing? What will be here? Okay. Now, of course, you want to give as tight as better this bound can is possible, right? Now, it turns out that there are several ways to actually prove this thing. So actually, it turns out that this will be actually order log n, which we'll just see right now, right? But it turns out there are several ways to proving this thing. Okay, so one normal way is to like opening up this this T of n by 2. So T of n by 2 would be T of n by 4 plus another 1 plus 1, right? Right. So I mean T of n by 4 plus 1 plus 1, right? I mean you are opening it up, right? Again from here we will go T of n by 8 and all. And then you say that it will come out to be, I mean this thing will this dominant term, this term would be T of 1 when like I mean you have done this say log n number of times. So there is 1 is say log n kind of thing, some, right? And in that case we will say this this T of n is order log n, right? This is a valid way of doing it, right? Hello.
Yes, sir.
Okay, now there are some things. So although it is valid, although this gives you actually an idea of how the bound would be, okay, but it turns out that this is not actually very formal. Although in many cases, I mean we actually follow this, but it's not completely formal, right? We are not giving you a rigorous formulations. Okay, so another second way, so this goes for first way of solving is, so another goes another way is like this, something called Master's theorem. So if people have seen it, well and good, otherwise I'll just briefly state what a Master theorem is. Okay, so you say that, see, this follows Master's theorems, this case number, so this value would be this order log n, right? Again there is a catch, is that Master theorem is not completely general, in the sense that Master theorem does not solve all possible recurrences. Hello, am I audible?
Yes, sir.
Yeah, so I mean only saying that Master theorem is our tool is not a very good idea, right? I will see when I'll probably at the end of the class we'll see that Master theorem doesn't handle all possible cases. So Master theorem is possibly not a very good candidate of solving in general formulas, in general recurrences. So finally, it is our good old friend induction, which will be mostly interested, right? So the best way to solve is somehow guess the solution and try to prove it via induction. Okay. Now this guess can come in from various ways. One is this opening up this formula, or you are using some generating function or some sort of technique to solve a recurrence, and then you some sort of guess, see, this is my solution, and then you prove it via induction. Okay. Hello.
Yes,
is,
sir, understood.
yeah. So we'll see couple of examples. So yeah. So for example, let's see this problem. Okay. So let's see this example one, which is this binary search recurrence. This T of n is T of n by 2 plus order 1 plus 1. So our initial guess is Tn is less than equal to C log n, right? Now note that when we write Tn equal to order log n, there is a constant hidden here, right? And since we are be putting these values exactly here, we actually need to specify this constant. It's not that it will hold for any log n. I mean, right? I mean, there needs to be some bound on this constant C. Okay. Okay. So maybe we start proving this. So if T of n is this, so this will be C log n by 2 plus 1, right? Now what we actually want to show, WTS means want to show. So we actually want to show that so there exists a constant such that C into log n by 2 plus 1 is less than C log n, right? Hello, this is okay, right? So there exists a C. There exists a constant C such that this thing holds, right? Is this okay? Hello.
Yes, sir.
Okay. Yeah. So it turns out that it is very like straightforward. So it is like so if we expand this left side, so it is like C log n minus C plus 1. It is like C log n, right? C into this thing, right? So I mean C for C greater than 1, right? I mean it will be like, sorry, it will be less than equal to, right? So C has to be greater than equal to 1, right? I mean, so that means let's take C equal to 2 or something, right? So this thing actually holds when you take C equal to 2, right? And since in order notation we do not like care about these constants, so I'll write it at Tn equal to order log n. Is this solution okay? Hello.
Yes, sir. It's
Okay.
like
Okay.
basic induction.
Yeah, but you have to be careful now. But we'll see one such thing. Okay. So this induction is for this binary search induction. So this recurrence relation actually comes from binary search, right? Binary search has been covered, no? Or hello? Hello?
So
Yes.
Yeah, it
we
is covered.
we know what's binaries.
Maybe not.
Sorry?
Hello.
Your
I think
voice.
most of us know what's binary search.
Nah, has it been covered in the course? I think.
Lecture has been posted of binary search
Yes.
on the website.
Okay.
Yes.
Okay, good. So you'll see. Okay. So let's see something little bit more involved compared to the last one, which is this. Okay. Let me stop. This is 2 into T of flow ceiling of n by 2 plus say order n. Now, so this is an induction. This is a recurrence relation that comes from something called merge sort. Okay. I think merge sort will be covered very recently. Okay. So it turns out that this will be, you'll see, you can say that this is the solution, right? So what will be our guess? Our guess would be somewhat like Tn is less than equal to like say some dn log n. Okay, is this okay? Hello.
Yes, sir.
Okay, so I can write it in this form. Since this order notation, I have to open it up and put a constant here, right? So Tn, we can write, so there exists a constant C, right, plus Cn. Now we'll see at the very end how this C and D are related. Okay, this will come up in the calculation, so let's not decide it beforehand, right? Now there are some things to note. So whenever, so first of all, whenever we use induction or something like that, right, it turns out that what we actually want to prove. So for example, here I want to express this Tn as a big O of something, some big O of some function fn. In that case, I have to prove, right? So maybe I write it here. Suppose I want to express my T of n as a big O of fn, right? So if we actually look at the example, look at the definition. So if we want to express it as big O of something, we actually have to prove that T of n is less than equal to some C of f of n. Okay, and this is the reason we have used like this thing. Oops. Okay, I mean, I am assuming less than equal to, or say here it is like I'm also assuming this is like T of n is less than equal to C log n. Okay, now again, what happens if we want to prove it like T of n, it will be omega of fn. I mean, in that case, we have to prove that it is like, I mean, if you want to prove it like omega of f of n, right, it will be like some C1, maybe this is C1, this is a C2 of f of n, right? And if we want to prove like T of n is some theta of say f of n, in that case we have to prove two cases. It is less than equal to C1 of f, some C3 of f of n, and it is greater than equal to some C4 of f of n, right? You understand my point? Actually, what we want to prove, that would determine what kind of guesses I want to take. Here we will see only big O notation, right? So I am actually assuming this is, we are guessing that Tn is less than equal to something. Okay, so this is okay, right? So maybe, yeah, right? Hello.
Yes, sir.
So what is the duration of this class? Hello.
Till 120, I think 115 or 120.
Okay. So yeah, we have enough
Hello?
time to go. Yeah.
Up till 115 or 120.
Okay. So we have enough time to cover it up. Okay.
120 precisely.
120.
Okay. So we have enough time. Okay. So so let's see this thing now. Ceiling of n by 2 plus say order of n, and our guess is T of n is less than equal to some d of log d of n log n, right? Now we cannot write this order as directly, so I am assuming, so there exists a constant, right? I mean, okay. Now this C and D will be somewhat related, and how it will be related, we'll like explore it now. Okay. And as I've said, this is this recurrence for March solve. Okay. Now there are some things here. So one obvious question is what happens when n by 2 is not integer? I mean, when the sealing is actually necessary, right? So it turns out that since we are actually sorry, since we are actually considering asymptotics, this +1 -1 doesn't matter, right? Also, it might be so whether n is odd or even, it doesn't matter. Also, in some cases, it might be useful if we assume, I mean, I'm not saying this is in general true. In some cases, right, assuming n is say greater than equal to some power of 2, right, it might be useful. And again, since we are considering asymptotics, I mean, it's good. Well, I mean, it's good enough. Okay, right? So let's let's jump onto this proving this thing. So T of n is like 2T of, let's say, ceiling of n by 2. I'm doing the whole thing, but it's not always in general necessary to like do this ceiling thing. So our guess is like Tn is less than equal to some dn log n, right? So if we actually unravel this thing, right, this implies that Tn, right, this is less than equal to 2 into d of ceiling of n by 2, right, log of ceiling of n by 2, right, plus cn, right? So if we like express it a bit more, right, so it actually, we can actually do it in this form. Okay, so one more thing. So ceiling of n by 2 is actually less than n by 1.5. You can actually check it this. Okay. In that case, if we express it in this form, I think we can write it in this way. This is like 2d of n by 2 plus 1 into log of n by 1.5 plus some cn, right? And if we like unravel it a bit more, I think it somewhat comes like this way. Maybe let's do this. I mean, maybe this is like d of n, so 2 cancels, log of n by 1.5, right, plus 2d log of n by 1.5 plus some cn, right? So if we do this once more, oops, this is somewhat this thing, right, less than equal to dn log n minus dn log 1.5 plus say 2d log n by 1.5 plus cn, right? Now we have to prove that this expression, right, is less than equal to d log n, dn log n, right? I mean, there exists, so we have to prove that there exists a c and d such that this whole expression, right, maybe is less than equal to this thing, right? This same as before, right? What we have done, right? This thing, right? So whatever we obtain after putting this thing, it should be less than equal to my original assumption, right? This is okay, right? Hello? Is the network got disconnected? Hello?
Yes, yes, it is.
So we can hear you, sir.
Yeah, I know. I mean, there is this issue. I mean, even if got disconnected, sometime I might not understand like whether it is disconnected or is it showing. I mean, it takes some time to disconnect it from my end. Okay. So I think this is a problem with Zoom, but yeah. Okay, so if we like do this bit more calculations, I think something of this form comes out. So I think maybe I'll Yeah, I think this is completely so I have done this. Maybe there is some constant and all thing, but I think you can like, so we have to something of this form, like in log 1.5 plus like 2 log 1.5 minus 2 log. I mean, to prove, to get a relation between D and C, we have to take it one on other side, right? So I mean, I think this is more or less comes out like this. So D into n plus 2 into log of 1.5 minus 2 log n, this has to be greater than equal to Cn, right? So I think if we take is like D is greater than equal to some 3C, I think this condition holds. Again, I am considering this asymptotic, so this minus 2 log n would not matter, right? I mean, this, because this n into the n is always more than log n, right? Hello.
Yes, sir.
Yes. So you understand my point, right?
Yes, sir. It
So n is always more than say log n, all
was,
right?
but
So I mean, so if we take, so D is greater than equal to some 3C or 4C, I think my calculation is wrong, not wrong. I mean, D is greater than equal to 3C, but you can check it out. I mean, yeah. So there is, so given a C, right, there exists a D, right? So there is a relation between D and C, right? Such that this like T of n is actually less than equal to D log n, Dn log n, sorry, Dn log n, right? And again, you are some sort of so Tn is like order n log n, right? Again, when we say these things, we actually hide these parameters, but when we prove, we have to show that there exists one such thing, right? Because it may be the case that no such thing is possible, right? When even in the very first, when I was actually giving you this counter example things, right, that n is not omega of n square, right? So those contradictions actually came from this sort of relations, right? So when you are proving it via this constant kind of thing is I mean, very necessary, right? So what was this issue that this 100n plus 5 is not omega n square? So the contradiction came that this n cannot be like upper bounded by some constant, right? So whenever we do this kind of calculations, I mean, it's very important to put these constants. Okay. And for this method, I mean, I have just this calculations looks a bit messy in this page, but the more or less the idea is whatever I have put it like replaced it in terms of this way, right? In this line, this has to be less than equal to my dn log n. And since we need a relation between C and D, I have like put them in two separate parts of, I mean, one is on left LHS and one is on RHS. So we did that, right? So is this okay? Hello? Is this okay? Hello? Please, I mean, speak up. I
Yes,
mean, yeah. So if you have any doubt, I mean, please just shout out, okay? Okay. Now I'll give you an example why putting this constant is actually very necessary, right? This very nice thing. I mean, what can actually go wrong if we are not very careful. Okay. So we know that Tn equal to 2 T of n by 2. So see, this is so we have proved like T of n is 2 T of n by 2 plus say order n. This is actually order n log n. And it turns out we can actually prove it to be theta n log n. Okay. So I mean, you can check it out. Now suppose someone claims this. Suppose someone comes and say, no, I'll give you a very good short proof, right? So this was a kind of a very calculation intensive proof and all. right? But suppose someone comes, someone claims, right? Say, no, this is not correct. I'll give you a very short proof and all. Say Tn is order n. Okay. Now someone checks like, see, this is order n, so this is also order n, right? When we are not carrying out constraints, so this is order n, right? So of course Tn is order n, so he must be right, right? But if you so let's for the moment like believe that this is actually theta. Okay, I mean you cannot beat that, right? So someone says like this is order n, right? I mean we have just assumed that Tn is the order n, and like order n plus order n is order n. So far so very good, right? I mean right? So what is happening, right? I mean this is certainly wrong. I mean just for the moment believe me that this is theta. I mean you can actually, this is a like a this, let's work it at home, right? This is actually theta. Okay, so we have proved the one way. You just have to so we have proved that Tn is less. So this thing, right, we have proved when we have assumed that Tn is says d of n log n, right? But as I have said, this was proof for only for big O, right? For theta we have to so also prove that Tn is greater than equal to some say kn log n, right? So please check this thing out, right? And right, is doable. I mean some sort of messy calculation, but certainly doable. Now let's come back to what I was saying. So someone claims this is order n, so order n plus order n. So what went wrong, right? This is certainly not true, right? So what is happening, right? I mean what is the like what is the bottleneck, right? So any idea? I mean just like you don't have to be right. I mean just shout out your any kind of idea. Anybody? I mean I'll explain it, but please I mean speak up and try.
In some sense, the constant should not be like C should not be dependent on n, it should be independent of n. And in the induction argument, we are essentially making it dependent on n. So that's the underlying contradiction here.
No, I think yeah, I think it is correct to some sense, but maybe with so see in this example, suppose maybe I go to this next page. T of n is 2 T of n by 2 plus the order n. Okay. Now suppose I actually like open it up, right? If this opening up, I mean until what point like this thing actually becomes T of 1. I mean some constant here times T of 1. If the number of steps to go from n by 2 to 1 is constant, right? If the number of steps to go from n by 2 to 1 is a constant, okay, then at every point note that we are adding this thing, right? So if the number of step is constant, so constant into some order of n, it will actually hide inside that constant, right? So suppose it was originally some C of n, and suppose number of steps is say some C prime. So in that case, my current thing would be like C into C prime or something like that, right? But if we actually unravel it, right, it is actually at every point it is actually getting half, right? So I mean from T of, I mean if we like see this like opening it up, so I mean it will be like 2 square T of n by 4 and so on. And similarly it will go, suppose it goes up to ith iteration. So at ith iteration say n by 2 to the power I, right? Suppose at ith iteration, right, n by 2 to the power I becomes actually 1, right? So I is log n, right? So if so the number of steps that it requires from going from starting to n by 2 to going down till 1 is not constant, it is actually log n. So at every point I am adding some this additive term, right? And we are actually adding it not a constant type, but as a function of n. In this term it is log n, right? So in total it is actually becoming n log n, right? So is this okay? Hello? Hello?
Yes, sir.
So how many times it actually requires to go down to 1? It is very much necessary. I mean, it is actually like it actually plays a role in this whole like computation, right? We see for this example it is taking log n, so n log n, right, which is like theta of n. But this won't be caught unless we get some constants. So this won't be caught unless we put some constants here, unless we prove it using some constants, right? So proving it using constants, say t of n is some c of n or something, that will actually catch it up. So although this constant like this d and c and this parameter like how this c and d will be related, it looks a bit like tedious work, but I mean it's actually necessary. I mean, you understand my point? I mean, otherwise this thing won't be caught, right? Is this okay? Hello? Hello?
Yes, sir.
Okay. So I'll just see once one more thing and today we'll end. Actually, this is a recurrence that we'll see sometime later. So this is actually something called a median finding algorithm. So this is the recurrence of that median finding algorithm. So this is a very celebrated algorithm. It will be covered later. So we have seen this binary search recursion, and we proved that it is order log n. And we have seen this merge sort recurrence, and we have proved that it is big of n log n, right? Now we'll see an example. Example 3. Oops. Right. So this is this very famous recurrence actually. T of n is T of, say, ceiling of n by 5 plus T of 7n by 10 plus 6 plus, say, theta of n. So this is a recurrence for something called median finding algorithm. This is a very famous algorithm. So we'll see that it gives you, so any kind of normal median finding algorithm takes order n, but this is a very nice sophisticated algorithm, not very sophisticated, but it's very kind of very nice argument. It gives you a better bound, it gives you a order n thing. Okay, so we'll try to prove that thing. So as before, I am not writing as a theta of n, I'll put a constant here. So more or less, this thing actually looks something like this: T of floor of n by 5, right? Plus T of 7n by, okay.
Isn't that a ceiling symbol on n by 5?
Yes. It is a ceiling symbol.
Yes.
Is it not? Maybe I'll.
No, you said floor, so that's why I asked.
Oh, sorry. sorry. Yeah, I messed up. So maybe I write it in. Maybe I write in a red. I think that is more visible. This is like 7n by 10 plus 6 plus some d of n, right? And I am our guess is t of n is less than equal to c of n. as before, we have to show somewhat a relation between C and D, right? But let's not go it right now. And I mean, what relation of C and D it will be required, we'll see when this calculation actually unravels. Okay. So T of n, if we put it here, is becoming C of n by 5, right? I mean, ceiling of course, plus 7 Cn by 10 plus 6 plus Dn, right? So this is like C of n by 5 plus C, right? Plus say 7 Cn by 10 plus 6 plus Dn, right? This implies, I mean, if you do these calculations and all, maybe I'll write it in small, I think, otherwise I can fit in the paper. So this is becoming 9 Cn by 10 plus 7C plus Dn. Okay. Now, as before, I want to prove it is less than equal to our original Cn, and we want to find some relation between C and D, right? So this is our goal, right? Is this okay? Hello? Hello, again the connection. Hello?
Yes, sir.
Okay. Sorry. Actually, it has happened to me couple of times, so sometimes the network got disconnected. So I'm always a bit more careful that, I mean, yeah, sorry. So I'll again like put this C and D times this all these terms with C on one side and all the terms on D, I mean, which is only one here on the other side. So we have to get us D and N such that this is like, I think it will be 10. So it is like 10 minus 7C, right? So basically, like if you take like this is like C of like n by 10 minus 7 or something. So basically dn by say n by 10 minus 7 is less than equal to C, right? So let's assume that for the moment, let's assume that n is greater than equal to 70 or something. Okay, we'll see how it will help. So if n is greater than equal to 70, so I can actually write it as a 10 dn by n minus 70, which is less than equal to C, right? Right. Yeah. Hello. This is okay, right? So, I mean, yeah. So I think if we take like if we assume, so I needed this n is greater than equal to 70 for like this thing, otherwise would become negative, right? This denominator term, right? So it implies that I think, okay, 10 dn. Okay, maybe I think maybe if we take C is greater than equal to 20d or something of this form, then what would be the value here? Maybe it will be something of this form, right? It will be something of this form, like 10 dn by like n minus 70 is greater than equal to 20d. So I mean n minus n by 70 is less than 2. So I think n has to be greater than equal to 140 or something, right? So if you take any value greater than n greater than equal to 40, so this obviously this denominator, this issue of that denominator might become negative actually goes away. So if we take say n is greater than equal to 140 and this condition, right, our Tn is actually order n, right? So this is actually this 140 is our n naught, okay? And this is this parameter, right? So is this okay? This is a bit messy. I think you can actually even more optimize it. Okay, so this is okay, right? So maybe I recap it once more. So this is my recurrence relation, original recurrence relation, right? And so this is in theta, so I am assuming some constant and all, and my guess is like Tn is say C of n. So I plug it here, and finally it all boils down to finding C and D such that this holds when n is large enough. And so this whatever remaining is this calculation. So it turns out that whenever this n is greater than equal to 140, and if you choose some C is greater than equal to 20D or something, right? So we can actually prove this thing. So is this okay? Oops. This is okay, right? Hello? Hello?
Yes, sir. Yes, sir.
Everybody, it is okay, right? So this
Yes,
is
sir,
also a
yes,
very
yes,
famous
yes.
relation for this median finding. Yeah, someone was saying, sorry, I just got we started talking simultaneously. Sorry, yeah, sorry, what, yes, somebody is saying something. Yeah, hello? Hello?
No, sir, I think I was just saying it was okay. Like we can hear you
Okay.
and we understood.
Okay. So if any point you have doubt, like just shout out, okay? So we have seen till now what you have seen that this thing, right? We have started with big O notation, then we saw big omega and then theta, and we saw 3 examples, right? And we have also seen this seam and little o and little omega, and we have gone through 3 examples. One for this binary search recurrence, which is here, t of n is t of n by 2 plus 1, right? And this the second thing is this merge sort recurrence relation, right? So tn is 2t of ceiling of n by 2 plus some order n, right? And it turns out that this is n log n. And we saw that final thing, this is this this median finding recurrence, right? And as we have seen, like this constants actually plays a role. I mean, uh, proving it formally, right? I mean, even with induction, I mean, these constants actually play a role, right? And okay, I mean, just putting constants would give us this this merge sort recurrence to be order n, which is not true. Okay, and yeah. Okay, so since I have some small amount of time, I'll just give you 2-3 properties. This is okay, right? I mean, class is not over, right? Yeah. Okay, just 2-3
120, sir.
Yeah. So I'll certainly finish.
Go through Master's theorem in detail.
No, master
Or-
theorem we won't prove, but I'll just state it.
Yes,
So,
and some applications of that, so that would be good.
sorry.
Some applications of Master's theorem as well. So we saw induction is a proof. So if you can.
But master theorem is not a proof. You understand my point? I mean,
Yes,
is not a proof.
some recurrences prove using Master's theorem. Some
Yeah, I
examples
think
of-
that is obvious. That is okay. Maybe I'll just go. Maybe just see. So just 2-3 before just going to 2-3. 2-3 properties of like this big omega theta and big O. So one first property is, suppose Fn is order Gn and Gn is order Hn. This implies that f of n is also order of Hn. Okay. Second thing is, of course, as somebody has pointed out, if n is order of g of n. Right. And of course, like similarly, right. And okay, yeah. So if n is like, say, theta of g of n, which implies that like gn is also theta of f of n. And there are also several other things. I mean, you can read the CLRS book. I mean, there's this big O things and all, little O. There are some other relations I don't exactly recall now. but I mean these proofs are very easy. I mean you just have to explore it a bit more. Okay, so yeah, so maybe I'll just state the master theorem and see 2-3 examples. This is a particular type of master theorem. So we are not proving master theorem. So there is a nice proof in the CLRS book. Okay, so please look it from there. I mean, it's a tree kind of proof, but it's very well written. I mean, yeah. So I think there won't be any doubt. So if there is a doubt, so please feel free to contact us. So there are several variants of they are more or less same, but there are some slight changes here and there. Okay, so this is a slight variation of the theorem that I generally like, but I mean it depends upon you what version of master theorem you will like. Okay, and so this is theta of n to the power k log n to the power p, and like where a is greater, so these are these conditions: a is greater than equal to 1, b has to be greater than 1, k is greater than equal to 0, and p is a real number. Okay, then if this is the case, say there is this condition 1, if a is greater than b to the power k, then t of n theta of n to the power log a base b, and if a is equal to b to the power k, if p is greater than -1, t of n is theta of n to the power log a base b. This will be log of n to the power p plus 1. If p is equal to -1, then t of n is equal to theta of n to the power log a base b log n, right? And of course when t is say less than -1, of n is say theta of n to the power log a base b, right? And also there is this third condition. If a is less than b to the power k, then is like if p is say greater than equal to 0, then t of n is theta of n to the power k log n to the power p, and if p is less than this, of course t of n is say what should I say, to the order of n to the power. Okay. Now, of course, you see that this is a very special type of recurrence. It solves very special type of divide and conquer kind of, which you'll see. I mean, this theorem only holds when my recurrence relation is actually of this form. But there can be several other recurrences, right? Say t of n is t of n minus 1 plus something, say 1 or something like that. In that case, directly master theorem doesn't work, right? So let's see some examples. I mean, so if we see this thing, so I think I'll just scale it out maybe. Okay. So for example, right, the t of n is say 3t of n by 2 plus say order n square or something, right? So in that case, I think like what is a is like 3, b is 2, right? And what is the value of k? K is the value of like say 2, right? So we actually counts to the like a is less than equal to b to the power k case, right? And p is 0, right? So in that case, I mean, it goes to this thing, so which is like theta of n square, right? This like this 3a case, right? Case 3, right? Is this okay? Hello? Hello? Oops. Yeah. Hello? Is this okay?
Yes, sir.
Hello? Can you hear me?
Yes, sir. The connection's fine.
Okay. And also let's see one thing. I should have written it a bit smaller. Sorry, I'm going to the next page. Sorry, I mean it would be better if I had written it smaller. But there's no space here. Let's see, for example, is example 2, right? So in that case, suppose I see another example kind of thing. Maybe we'll give you a different kind of thing. So t of n, right, is like say, what shall I say, square root t of n by 2 plus log n kind of thing. Okay, so what is the value of a? A is square root 2, p is 2, right? And say k is 0, right? And p equals to 1, right? So a is greater than b to the power k, right? So in that case, right, yeah, so t of n would be the first case would be theta of n to the power log a base b, which is like square root n. I mean, I'm using this first case, okay? This case 1, this case, okay? Theta of, right? Let's see one small thing. So if you put like this thing, right, this thing, what shall I say, example 3, so t of n is 2t of n by 2, right, plus say order n, so I can write so this is theta of n or something, I mean, yeah, so this will also turn out to be n log n. Okay, now let's see an example where this relation does not work, right? So for example, my recurrence relation is of this form, okay? Say t of n, like say 0.5, right? T of n by 2 plus 1, like a is less than 1 here, right? So at least this version of this thing. So here we have assumed this a is greater than equal to 1. Oops, sorry. So here we have assumed that a is greater than equal to 1. So this version doesn't apply. So there are several variants of Master's theorem which changes these conditions a bit and more. So I think in CLRs there is a definition with epsilon and all, but more or less this is same, right? So again, say for example, I define, so here, right? Here, whatever this first term with t, right? Other than this t term, whatever I am having is like additive term, right? Now what happens, I have this something like minus over there, okay? So for example, example 5, right? So let's put it this way. So maybe like, let's see, Tn is like 5t of n by 2 minus n square log n or something, right? So this doesn't hold, right? So the whole point of this thing is like, although master theorem is a very useful tool for initially guessing what would be the solution, right? Hello? Hello? Hello?
Yes, sir.
Yeah. So initially, so master theorem can be very useful for guessing kind of thing. So it certainly does not solve all kind of thing, right? So for example, like exercise 6 is like something like t of n is t of say n by 4, n minus 4 plus say some theta of n, right? This certainly doesn't fall into the conditions of master theorem, right? So although master theorem is very useful tool for initially guessing it before we prove it via induction, it certainly does not like solve all the cases, right? Now there is a slightly general version of master theorem, which I won't say, but there is some, so you can see it in this Wikipedia, which is called Akra-Bazzi method. If I think I'm pronouncing it correctly. Spelling is also hopefully correct. Akra-Bazzi theorem, right? It probably covers conditions more than master theorem, but again, I mean, see from Wikipedia. But again, this also does not solve all cases. Okay. So maybe I think it's time, but let's just let me just briefly recap what we have covered. So in the very beginning, wait, what is happening? Okay, in the very beginning, I have started with this thing, right? These order notations, right? So we have seen these big O notations, one example. Then we saw this big O notation, right? Then we saw this big omega notation, right? And again this theta notation. So roughly big O gives you an upper bound of any function, and big omega gives you a lower bound, and theta somewhat bounds this function between two C1gn and C2gn, some two different functions, right? And we also see some slight variant like little o and little omega, and this function which is called sin, right? And this is more or less rough kind of order wise comparisons between various common functions. And of course, I mean, you can put any set of functions in between this less than symbol, but this gives you a what all idea, like what are the orders and all. And also this thing also holds for some. So since we are considering asymptotics, we are only considering when n becomes large enough, so when n goes beyond some threshold. Okay. And finally we saw three examples, one for this binary search recurrence, right, and prove it by induction, and then this merge sort, and finally this median selection, median finding recurrence, right? And I briefly explained some, I think, properties and this master theorem. Also master theorem doesn't work for everything. Okay. Yeah, so this completes, I mean, what I wanted to cover. So if you have any doubts, so maybe you can ask. Hello.
Yes, sir.
Yeah, so if you have any doubt, I mean, you can ask. I mean the class ends, I mean, you can leave. I mean, it's your, I mean, you're free to leave.
No, sir, we understand.
Okay. And okay, so if there is no doubt, I'll probably end the class. So maybe I'll stop the share. So I'll upload this PDF. So these videos will be uploaded anyway, and I'll upload this notes in this class. Okay. And yeah, so this is,
Thank you.
yeah, sure.